This is the first video for our waves unit, and it is going to be discussing a lot of the properties that all waves have. And so the essential question here is, what is a wave, and what properties do all waves share with one another? So waves in general are energy that are moving through space. And when I say space, I don't just mean outer space. I mean just a space. Of course, it could include outer space, but for a lot of the things that we'll be discussing in this unit, I'm going to be sticking to us here on Earth. Two things that all waves have. One is a wave source. That's basically something that is starting a vibration. And so that could be a person, that could be an object, that could be the earth itself. It really just depends on the example. A medium is something else that all waves have. Basically, waves travel through certain materials. And so the medium of a wave is the material that the wave is in or going through. This could be the air. It could be a wall. It could be a glass window. It could be anything, really. This image down here, it's asking you, says, does the medium move from one place to another? No, it's actually like the wave that's traveling through the medium. And so it's kind of like you would think kind of one way or the other, but it's actually the wave itself is traveling through that medium. It's not the other way around. Here are a couple of examples for you. So if you look on at this picture, there is a wave being created. And so the source of that is this awesome cannonball person. So that person is actually creating that wave by jumping in. The medium is water. So that's where that's the object or thing that the wave is moving through. This next one. Look at this awesome thing. So our source, again, it's this person, this awesome physics dude's hand. That hand is what is generating that wave. That's causing the wave to begin. The medium for this is an interesting one. It's the gummy bears, the chopsticks, and that tape doodad contraption in the middle. And so that is actually what the wave is traveling through. Let's see. So this next piece, a couple of other terms that you need to know in order to be able to properly identify like parts of a wave and how waves, I guess, begin and how they behave. So a wave pulse is basically a single crest or trough. That's like the top image or the top part of this image. And so a crest is basically this upward like mound or hill you can see in the image below. And so a crest is one that would be moving in the upward direction. A trough is one that would be moving in a downward direction. And I'll show you an example of these in the next couple of slides. But a wave pulse is just a single crest or trough. And so wave sources can create wave pulses depending on how they create that wave or how maybe they move. Now, periodic waves, a little bit different. It's a bunch of full waves, like a complete wave, back to back. And so what happens here is there's like continued crests, that upward like part on the wave, and then followed by troughs, the downward part. Wave pulses, again, it's that single burst of energy from one side of a medium to another. That creates that wave. And so it's just keep thinking of it as one, like a single burst of energy. Now, the energy in a pulse can be measured by something called its amplitude. And so when you think of a wave that has high amplitude, you can say that there's a lot of energy in that wave. Now, specifically when we say, when we're trying to measure amplitude, we measure it from equilibrium. And in the next couple slides, I will show you in a picture what that actually, where that equilibrium is. But when you think of the word equilibrium, I want you guys to kind of think of, it being almost balanced in a way. And so there's a lot of ways you can describe this, but that's one way that I like to think of it. Now, there is a way to create a positive pulse and actually a negative pulse. And so a positive pulse, it's measured in the upward direction in meters from that equilibrium, basically that flat state. And so a positive one would have a positive value. So something like +2 meters from that equilibrium. A negative pulse would be in the downward direction. And so in the next couple slides, again, I will show you some examples of this. Now, the shape of a wave, I generally focus on the top wave in the image below, but the shape of the wave actually also depends on the movement of the wave pulse, or I'm sorry, not wave pulse, the wave source. And so it really depends on the movement of that wave source. And so there's all these different shapes that waves could generate. But the main one that we're used to seeing a lot of the times is that top one right there. Let's see. So this next piece has to do with something called propagation types. And so this, you can easily tell in that GIF, whatever you want to call it, the difference between these two types of waves. You could just look at it and see like, oh, they look a little bit different from one another. And so what happens here is there's a reason why those waves look different. So when we talk about propagation types, we're talking about the direction of that jiggle, like that wave source. How is that like wave source generating this wave? And so that jiggle, we're looking at that and comparing it to the direction the wave pulse moves. And so if you notice in both these images below, for both these types of waves, the wave pulse is moving from the left side of your screen to the right side. And so the direction of the jiggle will either make it so that a transverse wave is created or a longitudinal wave. Now, if you have your little slinkies we have that like we've given you in your kits, or if you just have a slinky at home, feel free to try this out and see if you can generate these two types of waves. And so a transverse wave, the medium that the wave is going through vibrates perpendicular to the wave velocity. And so if you look at this image of the transverse wave, do you see that like the medium itself and like the wave itself, they're perpendicular to one another, and it creates almost that little kink in the wave. Now, a longitudinal wave, a little bit different. It's not perpendicular. It's parallel. And so the medium is vibrating parallel to the wave velocity. And you can see that again in that image. And so the way to generate these types of waves with a transverse wave, that pulse is going to be, that initial pulse from the wave source is going to be perpendicular to the direction of travel. So that, let's say it's a person that's messing with a slinky, they would probably move that slinky up and then bring it back to normal to create that type of wave. For a longitudinal wave, that wave source on the left side, instead of moving the slinky up, they push it forward. And so you guys can try doing this to see if you can, again, generate this yourselves. Other types of waves that we have like that we don't really talk about in freshman physics, but they're definitely different types. But there's Rayleigh waves, and that's basically an example of when the like medium vibrates in a circular motion compared to the wave velocity. And torsional waves, it's a twisting motion instead. So those types of waves I want to share with you so that you know that those types of waves or propagation types, do exist. But the main two that I wanted you to focus on were the two that I have kind of listed above. All right, this is the part of the slideshow that I wanted to kind of go through and show different pieces that I kept saying, hey, I'm going to come back to that in the next few slides. So to be able to identify different parts of a wave is very important, because how can you describe a wave and the things that are happening and the properties it has if you don't know how to properly identify aspects of it? And so I had mentioned before in class that this topic itself, there's a lot of terms you have to know. And so I suggest if you want, make some flashcards and revisit these terms often. So the crest, again, I mentioned before, it's the highest point of a wave or highest pressure location. And so in this in this image, the crest is basically, if you look at the highest parts on the wave, it's basically, there's one right here, there's a second one right here, and a third one right here. A trough is the opposite of it. It's the lowest point of a wave. And so it's all the way down here. There's three again, 1, 2, and 3. Now, if you wanted to measure the amplitude or the height of the wave, remember I mentioned that term equilibrium, or the middle of the wave. So here is where equilibrium is on this wave. So our wave is this blue line that we're seeing, right? So equilibrium is basically that middle part of the wave, or it's where basically, and actually let me point it out to you. If you look at this black line all the way that cuts or slices this wave in half, that's equilibrium. So your amplitude, you're measuring the height of the wave from that black line. And so if you notice here on this last crest right here, here's the amplitude of this of this wave right here. And again, that's how much, like, the energy of the wave. Now, a cycle is one complete wave. So that's one full crest and one full trough. And so let's see, where was that? Here we go. So a cycle, here's one full crest, and then here's one full trough right there. So the other piece I wanted to show you on here is a wavelength. It's a little bit different. So if you notice, it's from one crest to the next crest. You could have also done it from one trough to the next trough. So wavelength and cycle, they look similar, but it's actually, they're a little bit different from where they start and stop. So I think that's mainly it for this one. And the one thing I forgot to mention, if you guys notice, I mentioned this black line was our equilibrium, but the direction of travel is also something that I tend to forget a little bit about. And so that truly is basically just telling you, hey, the wave is moving in this direction. It's as simple as that. All right, our last thing, and this is something that will kind of follow through into our next lecture, wave amplitude. I've mentioned it a little. It's related to how much energy is in each wave pulse. And so that is why we kind of waited to talk a little bit about waves until you had some background info on energy, because they're very closely connected. So this is an important variable because a wave is energy. And the thing is, like, us as humans use these types of waves to move energy from one place to another. If you think back to all the little examples we've done in class of energy transformation, a cute grandma at the top of the hill deciding to roll down because, I don't know, she likes to roll down hills, or a car coming to a stop, an alarm clock going off. All these things are connected to waves, and us humans we're able to function and do things like in our everyday lives because of these waves. Oh my gosh, science is so cool. All right, low amplitude, this adorable baby making little waves in a little kiddie pool. That's not going to have a ton of energy, right? That little baby is not going to be able to produce very powerful wave pulses, as opposed to this insane tsunami that the source of it obviously wasn't a cute baby, but it's our Earth. And so this tsunami that's created, it's literally a wave, and it creates, or not creates, but it has a ton of energy. And so that's kind of the main pieces I wanted you guys to get from this video. So let's revisit the essential question. I want to make sure you guys know what is a wave, and then what different properties do all waves share. All right, thanks for watching, my little ones. Here's a little adorable comic strip for you, back and forth, making waves, tidal wave. And then it says, beats me, Mom. Maybe the seal around the tub leaks. Ooh, lots of energy in this wave. All right, my little bubbas, enjoy. Have a good day. Oops.